We're going to talk about points at which the derivative would not exist. So I have a graph that's been drawn here, and I have these points A, B, C, and D. These are different x values. At each of these x values, the derivative is not going to exist. And let's go ahead and talk about each of these, and we'll talk about why. For A, we see here that it's definitely connected, it's continuous, but just because it's continuous, that doesn't mean the derivative exists. If I wanted to find the tangent right there, if I'm at a point, then I don't know exactly how to draw that, as far as I can draw that basically several different lines could all go through that same point. So whenever you have it coming to a peak, that's called a cusp, C-U-S-P, and if I have a cusp there, that's a place again where the derivative is not going to exist. The second one is here. If the actual value is undefined on the original function, that means it's also going to be undefined on the derivative. So at B, that's another place where we can't take the derivative. Now, there's a word for this. If you can't take the derivative at a certain point, instead of saying that, we're going to say that it's non-differentiable at B, or it's non-differentiable at A. That means that you can't take the derivative at that particular one, so we say it's not differentiable. Okay. For C, now C looks like it could be okay because we don't have any open circles or cusp or anything. However, at that point there's a vertical tangent line. So whenever I have a point where there's a vertical tangent line, then that's another place where the derivative is going to be undefined. So anytime the line goes vertical, not differentiable at that particular point. So at C, it's not differentiable because you have a vertical tangent. At D, graph is not connected here. So that's another place where it's not going to be differentiable either. Now the reason why that's the case is because when we do derivatives, remember that they're always based on the limit process. So the derivative from both sides have to approach the same thing. If the derivative, or if the limits coming in from the left and the right are different, then that means that the limit does not exist, and if the limit doesn't exist, therefore I can't do a derivative. So again, if I have a separation here where it's not continuous, then that's a place where it's not going to be differentiable. Okay, we want to find the domains where the graph is differentiable, continuous but not differentiable, and neither continuous nor differentiable. So this problem is going to cover this idea, and we're going to do that by reading these values off of a graph. Domains means they want you to find the x values at which each of these situations occur. So first thing, part A is asking us for what values is the graph differentiable. So the graph is going to be differentiable any place where there's not a corner. So I know it's not differentiable at -1, and I'm also not allowed to take the derivative at a place where the graph splits. So if there's a disconnect there, I can't do that. And it's also not differentiable where there's an open circle. So let's go ahead and write the interval for this. First of all, between -2 and -1, where -2 is included because it's closed. -1, we can't include that because, again, it's a place where you have a corner. Then it's also differentiable between -1 and 0. 0 we're not going to include because, again, there's going to be a separation in the graph. Then we have another one between 0 and 2. Again, 2 is not going to be included here because it's an open circle, and 0 is not included even though it is closed there. Okay, we're not talking about actual domain of the function, we're talking about where it's differentiable. Differentiable does not happen where there's a split in the graph where it's broken. Okay, so again, 0 is not included there. And then 2 to 3, that's another place, and 3 is going to be included there. So these are the intervals for which it's going to be differentiable. Part B asks for what places where it's continuous but not differentiable. That actually occurs at one spot only, and that's going to be here at -1. Now, there's no closed circle at that point. That's okay because the line is actually solid. If the line is solid, that means there is a point that's going to be there. So it doesn't necessarily have to have a closed circle for it to be an actual defined point there. It is going through the line solid, so it does cross at -1. That's actually the only answer for part B, x equals -1. It's continuous there, but it's not going to be differentiable. That's the only place. Then the last one, a place where it's not continuous and not differentiable. Okay, that's going to occur at two places. That's going to occur at x is equal at 0, and also x is equal to 2. At that place, the graph at 0 is disconnected. Okay, and then over here at 2, it's not continuous either because I got to lift my pen off the paper and continue. So if it's not continuous, that means it's not going to be differentiable either. And so at x equals 0 and x equals 2, it's not continuous, it's not differentiable.